Hi, my name is Bob Grenier and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this Sunday the 7th of September 2025, where we are going to discuss the gas analysis that I did with my colleague and friend in Santa Cruz in California, one Alan Goldwater, of the samples that were given to me before I set off to America by Henk Urian that came out of his various experiments in glowing activity, VEGA experiment. And we are going to discuss my analysis and see if there are some reasonable conclusions. So, can you hear me? Are you there, out there in YouTube land? Let me know if you can hear my voice clearly, if it's too distorted or whatever. I've had to set everything up. Hopefully it's still functioning. Welcome, Boo Blazer. What a great handle that is. And Harrison Wooten. Misunderstood. Thank you for staying up. Thank you, Treeball. Thank you, Charlotte. Thank you, Paul Harris. You're going to like this, Paul Harris. I think we're on our way to understanding the power source behind the ball lightning. And I will give a little bit of a implications discussion at the end. But it's really rather satisfying if this is true, and we have a path to verification for it. But let's see. Hi, James HL, not HL. Okay. All right, whatever that means. So, the actual analysis video that was done, recorded in Santa Cruz, you can gain by going to this link here, and the data that we are going to be looking at today, and the application which you can use to view that data. If anyone has any problems, let me know. I am going to be looking at this under Parallels on a Macintosh. And so, hi David Boutelier, you're going to love, and Dan Moretti, you're going to love the next video, and this is a very recent experiment by Henk Urian in his VEGA experiment. And for those that are coming to join us in Prague, you will see the Jan Rak, who was mentioned by Eugene Podkletnov a couple of days ago on Tim's interviews. A version of the VEGA experiment there in Prague. So you'll be able to see it up close and personal. So here, I'll let this play here. Hi, Mela Fury. So this is a still frame. You can see how the intensity of the plasma is coming towards a pinch point, and it's split into 4 quadrants. And then it has this domed glow over the top. I'll just play this off there. Maybe you can hear his words. I don't know. We will see if this works.
Interesting plasma regime on the anode. This is fascinating. It's I had this extra electrode there. Well, you can see that's gone. I have to when I want to use that, I need a new one. But okay. I don't know what I'm seeing actually. I mean, it's changing from one to the other. It's a cone. You can see standing waves, and there's a very nice pattern on the anode. I'm not pumping, so the pressure is getting higher a little bit. Okay.
No, Boo Blazer, that was not a grape in a microwave. That is a ball of metal in as the anode in a experiment in glowing activity experiment. Definitely a glowing activity. Hi, Tartan Beardy. Right, and so we're going to look at the the data that underpins the data for the gas analysis, and we have to understand a little bit about the device used, the Series 2 MKA quadrupole mass spectrometer. A couple of points here is the electron energy here. So this will be from the data file that I have already shared. And you can see the electron energy here is 40. Electron energy 40 specifically means 40 electron volts, representing a low electron energy setting. Standard settings are often 70 eV. This was the energy that was used in the Binger and Huang gas analysis by the experts that work for the Taiwan semiconductor industry. But we're using 40 eV in this analysis. And lower values like 40 eV are selected to avoid interfering peaks in the mass spectrum. Okay, so this gives us a tighter spectrum. And what you see down the bottom here is a load of bars going from mass 1 all the way through to mass 100. There's some gaps in there. And this is actually the spectrum of noise that the electronics produces in the device. And when you study this data, it doesn't even get up to 0.01 in the y-axis here. And so I've gone well above that and set my noise floor to over double the noise level. Now I'm going to show you the application over in the Windows side here. And what happened when we were running the experiment, the element turned off, and so we get to see the noise. So the element turned off here. So basically we are looking at air plus noise, and then we are looking at sample plus noise, sample 1, and then air plus noise and sample 2, and then sample 3, and then just noise down here. And you can see that the noise here, whatever we look at here, we're not achieving more than 0.02. We're always below this 0.01 line here. So if I move this bar along here, you can see that this is noise levels down at 6.11 times e to the minus 3. Go and have a look at this peak over here, 7.72 times e minus 3. Let's see if we can find a higher one. There's one over here. Okay, and that is 8.51 times to e to the minus 3. So this is the noise floor. The other thing is, so what we do to adjust for that, we go in here and I'm going to set the noise floor to 0.02 here, as I showed in my slide. And basically, as we go around this end where there's no data, we don't see any peaks in this whole area here. Okay. Hi, Magic Sound. I've just gone through the removing the noise floor. Okay. And so down the bottom here, when we turn on the device, it starts sucking in air, and it goes from not accurate level down to an accurate level down here where it stabilizes. Okay. And then we carry on a little bit, and this is all in sucking in the air. So this is looking at the air at this stage. And then suddenly you'll see these other signals coming in. And that's when we put in sample 1. And you can go and look at this on the video. And then we take out sample 1 and it pops back to air. And you can see how fast it changes. It just changes in like 2 scans. We're back, or maybe 3 scans. We're looking at the air, and then back within a couple of scans, you're looking at sample 2. Then back to air somewhere over here. That's air. Again, in a couple of scans, it goes back to the air. And then back when we put in sample 3. Okay. All right. Now, what you can see over this entire range, it doesn't matter whether we're looking at the air or we are looking at the samples, you do not see anything above 50. So we can go in here and go to view properties, and we can set the upper bound of the mass here to 50. Okay, and then that gives us a more clear representation of the data that's coming out of the mass spectrometer. Okay, all righty. Oh, not that one. Where are we? We need to go back here, and I need to press play again. It shuts that down. Okay. So then the ion energy here is 7 electron volts, and this is all in the data file that came out of it. So when it was recorded, it was looking at first mass 100, last mass 100. But it's good that we use this lower electron volt so we get less interfering peaks. So what we see on a peak really is around about that mass. So that's all good. And again, just to clarify, the noise never got to 0.01, even close. And so we've set it to 0.02 as our noise floor in the subsequent data. Now, what I next did is I took all of the valid samples, i.e. where it had settled and or it wasn't switching between for instance, the average air here and the sample 1. I've taken out these samples and then I averaged them, and I'll go into the spreadsheet now and you'll see what I've done there. Not on this one, in this one. So here we go. These are all for the air samples, and you can see it's really rather a large number of samples and across the 100 mass points. Okay. So this is where the atmospheric came in. It came in at a stable level by scan 10. And so from scan 11 all the way down to scan 291, we have got stable sort of samples on the air. And what I've done here, you can see I've sampled all of those and divided it by the number of samples, 281, to get an average sample for that mass number. Okay, so that should really tie that down to being average of all those samples. Again, the same thing was done for sample 1, and you can see here there were 111 samples, and then we have sample 2, and again we've got the average of those, and then sample 3, and we've got the average of those. So that's what I was doing there. And that gave us a series of averages that we will compare in a minute. Well, the spectrum for the air essentially was this. And you have atomic nitrogen, atomic oxygen. So you can see that the beam energy was 40 electron volts. The electron beam energy and the ion energy was 7 electron volts. So you can get some broken up parts of molecules. So we have here nitrogen. N2 is actually the strongest chemical bond. I thought for a long time that H2 was. By weight it is the strongest, but N2 is the strongest chemical bond. It's actually got 3 bonds in there. And so nitrogen is extremely stable. And that's why probably that it's there in the atmosphere in such abundance. Okay, so here we've got nitrogen, oxygen, so atomic oxygen. We have the OH radical here. There we go. And water. So that is your mass 14 for nitrogen, 16 for oxygen, the OH radical 17, and 18 at H2O. Then you've got nitrogen, and there's some isotopes of nitrogen. There's nitrogen 15, and you can see that this is a logarithmic scale, so this is vastly less than this. And this also might be a little bit of crosstalk because nitrogen is 78% of the air, and so you can expect it to be the biggest by far. You can see here oxygen is around about 20%, and you might have some isotopes of oxygen. This might be heavy oxygen or something else. But anyway, argon here at the 40 line, and CO2, this minuscule signal down here, practically the smallest of all of the signals, is this thing that everyone's worried about. It's actually 5.98, not 4, and that might be because there's Alan, myself, and a dog breathing away in that lab space, and so gets the CO2 a little bit higher from the anthropogenic production of CO2 in that lab space. So there we have that. Okay, now the sample one here you can see is has got a number of other peaks coming in. So the first peak that's coming in here is 2, which is hydrogen. You can see there's no 1 being detected here above our noise floor. And I think you can safely conclude, therefore, that the energy isn't sufficient to break up hydrogen to a great degree. Now, of course, you have hydrogen in water as well, and we know that we had some ice water in the form of ice in that container, so maybe it's coming from that. There's 12 here, which is carbon, okay? There's nitrogen at 14, there is oxygen at 16, and there is OH radical at 17, and there is the water here at 18. But as you notice, this 15 has come in, and what 15 is typically is a hydrocarbon, okay? It's a hydrocarbon. The nitrogen lines don't change so much. There's an extra lot of bit going on with 29. And we see this 31 dropping down. We see 33 coming in. And we see 30 appearing. Okay, we're going to have a look at that a little bit later. Now, the argon line drops a little bit. We have this 41 coming in here. And then around the CO2 massively leaps up. So we go from 5.98 to the -2 to 9.88 to the 0. So that's 2 orders of magnitude increase here. Much more significant at 44. And then we see the appearance also of mass 45 and mass 46. Okay, so that is very interesting. What is mass 45 and mass 46? Okay, we'll also look now at sample 2. So this is sample 2. Again, these are all single scans rather than averages. It's the software doesn't allow you to show an average. In fact, I haven't found out how to do it other than writing the data back into a file, which might technically be possible, but I don't think so. And I've not been able to do it. And if you try and do logarithmic data like this that starts at to the minus level, it's actually quite hard to do in spreadsheets. So this application is the simplest way to look at this data. Okay, anyway, so the important thing here is consistently across these, we're seeing this production of 43, 45, 46, 30, we're seeing the 15 here, and the 12 and the 2 across the various scans. Okay, there's also a little bit of a creepage in here of 19. Okay, so now if we actually got some synthesis here, and and Magic Sound says, is there any questions for him? I will talk about what you told me, but no, I think I resolved all of the outstanding questions. Now, in terms of if we are synthesizing matter in the VEGA experiments, and certainly it would appear from the VEGA Valley and other experiments that have been conducted in the VEGA experiment, we are getting magnetohydrodynamics for certain. We have the teleportation, the flux loop, the Hutchison effect going on. We have these regular arrays of matter being destroyed and these iron-rich crenellated spheres and these particular structures, which Matsumoto, of course, observed, and in the electronuclear regeneration that he coined the phrase for, he saw conventional elements such as carbon, oxygen, and iron being synthesized. Carbon, oxygen, and iron. Okay? And he described it as whatever the matter is gets collapsed into a point of electronuclear collapse. And the matter then travels through a wormhole, which we physically observed on the cardioid infarction sample. And then you get the production of hydrogen, carbon, and oxygen. And you get the production of titanium and iron in the center. So on the outside, you get this hydrogen, carbon, and oxygen, etc. And then in the center, you get this titanium and iron. So we actually saw these carbon tubes. We've seen these products in various experiments. And the actual products we also have seen in the Vega Valley, this is from 10th of May 2022, in this classic shot of the broken up ball lightning-like structure. You have the iron and oxygen core, the silicon and oxygen around the outside of that, and the calcium and oxygen around the outside of that. And then this blended material that you see between here is predominantly carbon and elements in between. This major fractions here of iron, silicon, and calcium were seen in the physical review letter, the only spectrum of ball lightning. Of course, they're seeing nitrogen and oxygen. Those two are in the air. And I believe that oxygen and hydrogen are the fuel. And you're going to see why I think that in a few minutes. It's going to be a quite short experimental review here, or rather data review, but I think it's probably one of the most significant ones I have done since the start of this journey, if it turns out, in fact, to be true. So the iron and silicon and calcium, of course, they're all constituents in air and in soil, rather, and someone might say that it's come from the soil, but the fact that this broken up ball lightning on this zinc copper oxide background gave these perfect signatures, and we've seen this over and over again. I think this is really the signature of ball lightning. Now we also know that the iron-rich crenellated sphere itself has a hole in it, typically, of which it spews the internal contents. And on a separate area of the Vega Valley, we saw this little iron-rich crenellated sphere. You can see another one here and another one here. But this one had two aspects to it. It set out this tube of material, which is exactly as described by Matsumoto. It's a tube, and it's predominantly carbon. The tube here is 84.8% by mass carbon, and then it's 13.343 oxygen, and then the sulfur, copper, and zinc will be seen through the bottom of that. So if you adjust for the oxygen and the copper and zinc in the substrate, because some of the beam energy will go through and give you photons from the substrate, then you could argue that almost all of this tube is carbon. But what have we got here on this head? Before we go there, we'll look on the outside of this iron-rich crenellated sphere, and we can see iron and silicon, just as we observed in the previous slide here, iron with silicon, okay? So the silicon comes on the outside, so much less, but some oxygen and iron in this FeO2 kind of approximate ratio. Now, if we go and have a look now at these two toroidal discs that are being ejected here from the hole on which the carbon tube was first ejected, then we can see that this here, from this spectrum here, has a atomic concentration of 7.655 atoms of titanium. Okay, and titanium is the fusion of CO2. And here we go, we have here 21% by weight. So a large proportion of the mass that's actually in these structures coming out of the hole is titanium. Again, looking at another spot here, we have again titanium here, and we also have some calcium going on here, and a range of these elements that you get this stellar synthesis, carbon, oxygen there, but aluminium, silicon, calcium, titanium, iron, okay, in here. And then again, a look at the trail there. It's predominantly carbon and oxygen with the copper and zinc showing through, but also we have a little bit of calcium there. So these same kind of signatures turning up. Now, in the next slide, unfortunately, when I imaged this, the SEM did not have a EDS detector, but this was from the binge. Thank you very much, Black Tie. It's really kind of you for that £20. The VCS 5RT. This was the one of the most heat-producing, if not the most heat-producing reactor in one reactor configuration of Binge Ren Huang. It produced this iron-rich crenellated sphere, same exact morphology as those observed in the VEGA experiment of Henk Uren and others, but it had this darker material inside, which normally indicates a lighter elements with what look like toroidal structures in there with lighter flecks in there. Unfortunately, I couldn't look at this as I said, on that day, but in a separate reactor that was given to me at a later time, the 41B, we found a broken up one of these structures showing the golden ratio inner and outer part of the iron oxygen rich outside. And these toroidal structures, which are predominantly carbon and oxygen, okay, but they have whiter areas in there, and the whiter areas are in fact this titanium, okay? So the fusion of CO2 in the ratio that you observe it in there, which is CO2 approximately, if you fuse that together, you get titanium. So what I'm arguing is that when the wavelets of the coherent matter, when you do the coherent energy transformation, hit the normal vacuum energy state, it automatically collapses into the constituent ratios of the density of the wavelets of the coherent matter in there. And so you get these carbon, oxygen, and then where they are intersecting, you can imagine maybe you are seeing the titanium. Okay? Now, that is the formation of titanium out of the core of the iron-rich crenellated sphere. As you can see here, you are seeing some iron here in this section here. It's not a lot, but you have to go past calcium and titanium to get to iron. And we're going to see how that happens in a little while. Now, in the paper in Nature, which we are still discussing with the editors of Nature, who are, let's put it this way, not at the top of their game, shall I say. There was my proposal for the reaction, which is based on neutrinos, in this case an antineutrino coming in to allow for the simultaneous fusion of a proton, an electron, and 16 oxygen. This whole reaction is energetically favorable to go immediately through the what I would call the coherent energy transformation of the magneto-toroelectrical cluster, the fractal toroidal moment core, the topological monopole, and it produces the 17 oxygen here. Okay, and I've argued the precise reason for that is that all forms of oxygen are paramagnetic and uniquely paramagnetic in that way, and highly paramagnetic, and atomic hydrogen, whether it is with an electron, as you can look at it here, or without an electron, the electron's just there anyway in an electron cloud, they can, both of those things have a magnetic moment, whereas H2 does not. So you do need to split the hydrogen into atomic hydrogen, okay? And those come together. This was the proposal from one of the reviewers, which we put in as part of the peer review process. Although it's basically impossible for this reason. Sorry, not this one, I'm talking about 7. This one here, where you get a proton and an electron and 16 oxygen fusing to make 17 oxygen and an antineutrino. This is not possible because you need to have the formation of a neutron in this process, and you have to give it energy, and so you have to, and you also will produce a gamma. So this is not a possible process, in my view, but this is what the reviewer wanted to be put into there. And the focus of this paper was on the observation, and this is only hypothetical mechanisms and reactions to achieve the 17 oxygen required for reaction 8. Reaction 8 is 2 17 oxygens come together to produce 12 carbon and 22 neon. I have previously in another presentation reframed the John Bockris of Texas A&M and Sundaresan experiment that they did, I think, in 1995 or 1996 of carbon arc underwater, where they said it was 2 carbons and 2 18 oxygens coming together to produce 4 helium and iron 56 that explained the extra heat and synthesis of iron in their carbon arc experiment underwater. I've said you actually form 4 17 oxygens and they fuse and fission to 12 carbon and iron 56. The energy release is almost identical, and it would account for what they observed, but they would never have seen the carbon. So it's a similar process, and I think this whole process of formation of 17 oxygen and formation of elements from that those core building blocks and the synthesis of carbon and other elements is what is going on as a fuel source for LENR and also as a fuel source for other systems that involve water, like ball lightning. Okay, so 12 carbon and 17 oxygen. Why do I think that happens? Well, here are the reactions in order from nanosoft.co.nz, the reaction calculator I designed and Philip Power built for me. Thank you very much, Philip Power. In New Zealand, based off the Parkhomov reaction tables. And if you look at the reactions here, the first most energetic, which are the most likely if you're trying to squeeze it into a small box, and remember that is a small sphere, is the interaction of carbon-13 and oxygen-18 with the neutrino on the right, carbon-13 and oxygen-17, carbon-12 and oxygen-18. These are unlikely, and that's because look at the percentage abundance of 16, 17 and 18 in the crust. If you're having 18 here, that is unlikely to occur. And plus, carbon-13 is also very unlikely. And it's not a synthesis product of this process. You get carbon-12 out, you don't get carbon-13 out. So if you have no carbon to start with, as I showed you here, you end up by synthesizing carbon-12, whether you're getting neon or whether you're getting iron 56. Okay, so you don't have 12. 12 is by far the most abundant element. So these are more unlikely, although there is some natural abundance of carbon-13. So this could occur. Right. So before I go into this, and just complete this table, I need to show you what the output and my evaluation of the elements are that are going on in the mass spectra. So again, I showed you the average here, and this is what it comes down to. Essentially, I have, if I zoom into this, where everything is either negative, that is red in brackets, or it is very low, i.e. below my threshold of 0.02, I've kind of redded it out. These aren't redded out, but they're essentially noise as well, because they're below 0.02, which is my noise threshold. These are well above the noise threshold, and you can see over and above here, it's difficult because this is a negative. It's basically noise. So, you know, I've had to make this positive. It should actually be like this. I should actually have these in brackets by removing the negative symbol here, as I've got over here. So essentially there's 0 hydrogen in the air ordinarily, and there is a large amount of hydrogen relatively in the analyzed gas. Then there is 12 carbon. So for some reason, we are getting hydrogen and carbon. And we know from the work of Piantelli, he says protons come out of this system. And we also know from other people that are suggesting, and I have suggested, that carbon and hydrogen are produced by coherent energy transformations in the bowels of the Earth, and that is what leads to abiogenic synthesis of hydrocarbons. And so Matsumoto observed hydrogen and carbon coming out. So these two things could be synthesis products. 14 nitrogen, you can see here that on sample 1, it's actually below the amount of nitrogen that was in the air, but it's slightly above here. So this is not really significant. And essentially what I've done is, where it's not that massively significant, I've left it as not colored. The 15 nitrogen here, this 15 nitrogen is a rare isotope. It's still well below the noise level at this point here. However, it's massively above that in this area here. So what is it? Well, it is CH3. It's a hydrocarbon fragment. Now, when I start to see CH3, I think, well, is it synthesized? Because, like, you've got carbon and hydrogen, but is it likely to synthesize a hydrocarbon? Maybe. And maybe it could synthesize a hydrocarbon in the core of the structure. So if you've got carbon being synthesized in the coherent energy transformation system in the center of the ball lightning structure, and it's under intense pressure, it may actually start to produce a hydrocarbon fragment. So these are not significant. The 16 oxygen, the OH radical, and the H2O. When we get to 19, and again, there was nothing basically here, but it was positive at some level. It's 0.0004498. We end up with a reasonably significant increase in this. And what is this? Well, it could be hydronium, because we've definitely got hydrogen here, and it's not a single atomic hydrogen, but it's hydrogen, and it's bubbling through water when the gas is produced. So it could be hydronium, or it could be heavy oxygen water. That's at H217O, as observed by Bin Zhuan Huang. It could also be fluorine, but I don't think so. There's a proviso I need to make at the end of that, because of something that was used by Alan to test the gas spectrometer earlier in the day. But it's not really important for the point of argument here to focus on whether this is hydronium, fluorine ion, or H217O. Right, so 26 appears. Again, it's below the noise floor here, but it's more than double here, and here it is 10 times. This is an order of magnitude bigger and well above the noise floor here in these two samples from the gas sampled. And what is this? Well, this is acetylene, C2H2, and again, it's a fragment of a hydrocarbon. And could the acetylene be produced inside the ball lightning structure? I think it probably can, and I know someone that's in the chat that would probably agree with me. I'm looking at you, Paul Harris. Here, these are below the air sample. This is barely above, so we won't be really considering 27, 28. Again, to 29, we have a much larger, this is well above the noise floor here. And this is massively above the noise floor, and we've got factors here. So it's relatively above the noise floor here, but this is much larger. So again, C2H5, this is a hydrocarbon fragment. And here, again, at 30, we have a slight increase here, and this is ethane. So what we are looking at here is possibly the formation of hydrocarbons. This is abiogenic synthesis of hydrocarbons. Okay, let's go up the chain here. The 31, 32 are not significant. They're below atmospheric conditions. Okay, 34 again is below atmospheric air, and here is in 33 is barely above it. Okay, so nothing really of interest there. Again, same story here at 39, same story here at 40, same story here at 42. However, again, this is negative, so it makes it difficult. But here, this is very, very significantly above the background, but it's still not much above noise, because the noise level I set at 0.02, this is 0.028, this is 0.031, this is 0.044. However, this is the propyl ion. And similarly, at mass 43, this is C3H5 plus. At mass 43, you have C3H7 plus. Again, this is really starting to talk about fairly big numbers. This is 3 times the noise level. So I'm not going to get too excited about this. Not too excited about these 2 propyl ions. However, when we get to mass 44, we've got to think, because we see on average across all of the samples that Alan and I are obviously mouth breathers, heavy breathers, and the dog and maybe the cat as well contributed to this level of CO2 in the background air in there. However, look, this goes from 0.06 to 9. Okay, so it's 2 orders of magnitude bigger, 8.8, 8.2, fairly consistent across those in the same order of magnitude. This is either C3H8, that is to say propane, or it's CO2. Now we know it's CO2 in the air. It could be propane because the tank has formerly been used with propane. Now, I had a long discussion with Henk. The steel is known to not absorb propane. It had been used for a very, very long time. However, because propyl ions and this and this and this and this and this could all be fractions of propane, we can't discount the fact that it might be propane. However, where I'm getting really excited is this. Mass 45. It basically didn't exist. It was 0.000144. So it's more than 2 orders of magnitude below the noise floor on average across all of the samples. And suddenly it's 0.23, like an order of magnitude above the noise floor. Okay, 1,611, 1,259 times, 1,237 times. A significant signal here. What is this? Well, this, my dear friends, is quite likely, possibly, and it's almost difficult to believe it, 13C, 16 oxygen. I don't think so, because 13C is very rare, and I don't expect it to be that. But the likelihood here is that it's heavy CO2. Again, at 46, there was even less. In fact, it was slightly more, actually. But it's actually negative, so it's a lot less. And so whilst this is negative and it skews the numbers, if I actually made this... Yeah, anyway, this is negative. So this is basically infinitely more. And this would be super heavy oxygen CO2. So I don't know why that should say 12 carbon. I don't know why it's not saying 12, but it should be 12 there. That should be 12. Anyway, yeah, that should be 12, not 2. There's no 2 carbon. Ignore that. I'll fix that before I share the data. So this is actually more significant than this, okay, relative to the start point, although it gets messed up because the noise is negative here. Okay, thank you for your kind words, Silent G. So what we have here, essentially, is either dimethyl ether here, or we have another heavy oxygen CO2. Now, the thing is that this is in a plasma environment. It's both in a plasma environment in the sense of in the VEGA reactor, which is an intense plasma environment, and it's in a plasma or an ionizing environment in the mass spectrometer. So I don't think you're going to be synthesizing this dimethyl ether in here, even if we had propane in the tank. Okay, So, and the thing is actually that CO2 is a stronger bond strength than either water or O2. And so CO2 is very good at surviving. And so it's a good signature. So if this is heavy CO2, we can verify this in another run, and we either need to bring Mohammed to the mountain or the mountain to Mohammed. That is to say, we need to get the gas spectrometer to a VEGA experiment or a VEGA experiment to the gas spectrometer and do this real time, okay? And we need to scrub. If we can't do that, we need to at least scrub using calcium oxide the gas coming out, or before it goes into the mass spectrometer. If we do the scrubbing and we remove this massive increase, this 3 orders of magnitude increase of signal, and this is more than 3 orders of magnitude increase here of these, if they are absorbed, that is to say the CO2 is absorbed by the calcium oxide, the scrubber, then 100% certainly we are creating heavy CO2, which is a plasma system with magnetohydrodynamics doing exactly what is happening and that I predicted before it was observed through the magnetohydrodynamic process, through very detailed reasons and normal property reasons of the atoms and their molecules and their atomic states in the Binge-Wen Huang reactor, the subject of that paper. So if you go back to our paper here, I will walk through the entire process, and it's highly, highly logical. Okay, it's highly logical. It all follows the same logic. Right, so naturally speaking, 12 carbon and 16 oxygen are the most abundant elements that are in the Earth's crust. 12 carbon is 98.89% of natural carbon, and the 16 oxygen is 99.759% of the Earth's crust. Okay, so because carbon-13 is not abundant, reaction at the top here, which is energetically most favorable and most likely to happen when you're trying to squeeze it into that small sphere in the center of the magnetohydrodynamic structure, this is unlikely to happen. This is again carbon-13, again unlikely to happen. And of course, oxygen-18 is a rare isotope, unlikely to happen. So in a situation where you have abundant carbon-12, either because you have carbon-12 in the system or because you are synthesizing it as part of this process of either producing neon-22 or producing iron-56 from the Bockris experiment, from the Huang experiment and from the Bockris experiment respectively, you have carbon-12 and you have the oxygen-17 synthesized by this process here, the first reaction that you come across where you have either natural or synthesized carbon-12 reacting with oxygen-17 leads to silicon-29. And this is where it gets really interesting, because you've got to imagine that this process is going on in a massive way in the core of these reactors. So now we have silicon-29 in the mix, and more 17 oxygen being synthesized, and silicon-29 is the second most abundant element isotope of silicon in the Earth's crust. Okay, so we have 29 silicon and 17 oxygen. Well, looky here. The first 3 reactions here use rare oxygen-18, rare oxygen-18, rare oxygen-18, and the first 2 of those uses the rarest silicon and then the second rarest silicon. And then the third one uses the most common form of silicon. It's most of the Earth's crust, and it's the second most abundant element in the Earth's crust. However, oxygen-18 is rare. So the first reaction that comes, which is most likely when you've got a process producing this from oxygen-17 and carbon-12 to silicon-29, is the oxygen-17 and silicon-29 reaction, which produces titanium-46. Titanium-46 is the second most You're going to see a pattern here. Abundant element in the Earth's crust. Okay, what happens when you fuse that? Well, we'll come along to that in a minute. But anyway, we see titanium. Where did we see titanium? Well, we saw titanium. We saw it here in the core, along with, what do we see it with? Carbon and oxygen. Now, we don't know the isotopes, but we saw it with carbon and oxygen. Here, we saw titanium. It's the third most abundant element in the core of this structure. Where else did we see it? So this is in Benjamin Huang's 4-1-B. I expect that if we could have looked at this with EDS, this would have had titanium in it. We saw titanium in large areas of broken up material as spots, just like you see here in other areas of various cores of Benjamin Huang reactors. Out of this, from the Vega Valley, you see titanium. It is the third most abundant element, which is not the substrate of zinc here. So again, look at it here. Titanium, the third most abundant element in there other than carbon and oxygen. So that is, in my view, how it is synthesized. You get first the water provides hydrogen and oxygen electrons. The process combines those into 17 oxygen. And then you can get carbon-12 synthesized by this process or by the one that goes to iron, or you can get carbon-12 from the environment. There are other paths to carbon-12, but this combines, and this is the first most likely to get to silicon. Silicon is observed. It is observed here, you see, in the core, okay? It is observed here in the material coming out of the core, okay? So silicon is observed, and that goes to titanium 46, okay? Then the reaction which I showed you here that produces neon, here 22 neon plus 22 neon produces calcium 44, which just so happens to be the second most abundant isotope of calcium. Where do we see calcium? We see calcium in the outside of ball lightning. We see it coming out of the core here. We've got calcium here, okay? And we see here calcium. Okay, calcium is formed in these processes, okay? So calcium 44. Now, if we take calcium 44 and we fuse that with carbon 12, what do we get? Drum roll, iron 56. Calcium 12 and carbon 12 and calcium 44, iron 56. There is a massive amount of energy that can be yielded from this process. Firstly, there's a whole shed load of energy that comes from this. Then you get carbon 12 to oxygen 17, 21 million electron volts. Oxygen 17 and silicon 29, 21 million electron volts. Here, the two fusions of neon 22 over and above the energy you get from this reaction here is 25 million electron volts. And down here, when you take this calcium 44 and you fuse that with carbon 12, you get 19 million electron volts. This is so much energy. So much energy. Now notice, you've got the most abundant elements to start with. Carbon and oxygen here are natural, okay? Once you start synthesizing this oxygen 17, it is not only paramagnetic, it has spin because it's an odd nuclei isotope. So it is preferentially captured into the core. And so in my view, it's preferentially taking place in the reaction. And that is exactly what you're seeing here. I don't think you need to go through this process necessarily. In some parts of the wavelets, it will go straight there. But when you get past the initial experiment products, or rather inputs, you have the second most abundant element playing the principal role. The second most of silicon. The second most abundant isotope of calcium playing a principal role. The second most abundant isotope of neon taking a principal role. And the second most abundant isotope here taking a principal role. So it's all the second. So I think the reason they are the second most abundant element is because this process has gone on producing these second most abundant elements all over the world, right? And so this is we now have multiple sets of data that are 100% on magnetohydrodynamics, fractal toroidal structures that produce these iron-rich granulated spheres, out of which the same products are being produced. Okay, and the other thing I'd like to point out here is that once you have done this reaction, which is the key reaction, which involves water, okay, so this is essentially water as your start point. Then you can get this reaction by the fusion of this, which gives you the carbon to move forward, okay. You have no neutrino needed here, no neutrino needed here, no neutrino needed here, no neutrino needed here. So this is the stumbling block. You have to overcome the energy or you need to create the system that can combine protons, electrons, antineutrinos, and oxygen nuclei in the same box to produce 17 oxygen, and then you're off to the races, because you don't need to have it from that point. Once you've got the oxygen 17, it's just about the electrodynamics to keep it in there. Okay, so spin nuclei, silicon 29, spin nuclei, oxygen 17. Okay, so that is that. A discussion here, I've mentioned some of these points before. All of these could be fragments of propane due to prior use of propane in the tank, though propane does not add or absorb well into the material of the tank. One would need to consider all other parts of the vacuum system to sample jar pathway. At a stretch, they could form coherent energy transformations of elements likely heavier than iron in the tank, producing carbon and hydrogen with subsequent abiogenic synthesis of hydrocarbons. Okay, so I'm saying that we may have shown the process behind abiogenic synthesis of hydrocarbons from whatever material you start with, because it's not only you can put hydrogen and oxygen in there from water, you can start with every other element and it breaks it down through cluster decay. CO2 is more stable than H2O, which is more stable than O2, and there is carbon and hydrogen to spare, though hydrogen is light and may have vented from the chamber more easily. Carbon could be an hydrocarbon gas fragment in ionization. O2 appears to drop at mass 32 and 34. However, mass 33, which is heavy O2, 17, appears to rise or not drop as much as the other more common isotope elements. So let me just verify that when we go to our chart rather here. We go back to our heavy O2, 33 here, yeah. So, what did I say there? I said 32 and 34 are 32 and 34, 32 and 34. They drop, okay? But here, 33, which is heavy oxygen, which is O16, O17, or 17O, 16O, this actually rises effectively. So I think this is reasonably supportive evidence of the Binger and Huang observation in a system that is heavily reliant on water. And of course, it's difficult to get water out of everything. And so there will be some water in here. Just to close out on the presentation before a little bit of further discussion here, I need to go here. No, not there. Where is my presentation? Yeah. Alan used norflurane, which is 1112 tetrafluoroethane, as a test in the device. Now, what you see here are the spectrums of 43, 44, and 45. There's no 46 there. Okay. You also see spectrums here, very high signals at something like 69, and a very high spectrum signal at 81 to 3. Okay, and then some over 100. We can't see over 100. Let's go back to our data here, and we will reframe this to see over up to 100. And you can see that at no point do we see any, when we're either in the air or at any other point or in the noise at the end, do we see any contamination that would be commensurate with these spectrums. So I do not think the material in there, the tetrafluoroethane, contaminated it. And this process gas mass spectrometer is very specifically designed to quickly see changes in the sample port gas input. So I don't think that would be the case. Now, about the propane, then this is a mass spectrum, again, from NIST Chemistry webbook. You can go to the website here and look it up. It does have this 15 signal here that we talked about. It does have these spectrum around 28 here, and it has this huge peak here at 29, and it also has these peaks at 40, but 41, 42, 43, 44, but it does not have any significant peak at 46. So I don't think that this changes the conclusion. And what is the conclusion really? I think the conclusion is that Matsumoto was essentially right. Yes, hydrogen, carbon, and oxygen are produced from the collapsed matter. And also you get titanium and iron. And we have shown that you also get calcium. He also observed calcium. He says here carbon, oxygen, and iron. And that some of the products come from the inside of the ball. Some of it may come from the substructures of the overall magnetotoroelectrical structure, the fractal toroidal moment based structure of the overall electrodynamic structure. And when the matter is allowed to be freed from the binding forces of the fractal toroidal moment at the topological monopoles and fractions of substructures that have topological monopoles in them, they bleed out and they reveal what they are. And what you get is the density of the material is reflected in the matter from the wavelets. And the reason this is dim and dappled like this with higher concentrations of carbon and oxygen and then titanium is that it's wavelets. These are substructures that were probably, I wonder if there were these little tores, there was 48 of these tores in this bundle here that have all come out and kind of merged into this blob. It would be interesting to be able to calculate that or find that at some point. I don't know, or maybe there's substructures of substructures, who knows. But anyway, they do show this kind of, it almost looks like a sponge, where in some areas you've got the titanium, in others it's mostly carbon and oxygen. It is the fusion of CO2 effectively that gives you your titanium. Okay, so what are the implications of this? The implications are this. The water may well be the principal source of fuel, along with oxygen, for ball lightning. Okay, I've shown you the reaction energies that are phenomenal, that lead to the formation of silicon, calcium, and iron, which are the principal spectrum that were observed in actual real ball lightning and that we have physically seen coming out of blown up ball lightning structures in experiments of the VEGA experiment and as have come out of the Binge-Ren-Huang cavitation reactors. Okay, just to name two. So it's very clear to me that there are vast potentials for energy. Now, you could say, like, is the energy used to split everything up into bare nucleons and then they get reassembled, or are they split, as I believe, into principally carbon and oxygen and hydrogen? Hydrogen, carbon, and oxygen. Remember what was shown by Matsumoto. Hydrogen, carbon, and oxygen. These essentially, in my view, are the building blocks of most atoms outside of just a pure alpha particle. Okay, and so these are effectively cluster decay products of atoms, and I believe that that is what is going on. You've got a cluster decay in this vacuum gradient process, which excites atoms as they fall towards the topological monopole. And as they get in there, they essentially become hydrogen, carbon, and oxygen, but then they get built and the density increases of wavelets in the coherent core. And when the confinement fails inside that altered vacuum state and it hits the ordinary vacuum, they go into ordinary atoms based on the wavelet density. And if the wavelet density is increased, you get heavier and heavier elements formed, as was observed by S.V. Adamenko, and he details it. Basically, it goes up to iron, it stays at iron for a long time until what he describes as the electron gas, electron gas, nuclei, nucleon, density increases past a critical threshold, and then you get the synthesis of super heavy elements up to thousands of AMU. And so I don't see it specifically like that. I see it as an electron quark gluon plasma, coherent wavelet condensate structure in that as a magnetohydrodynamic structure. And it collapses out, and that's why you get those kind of structures being formed. And at some point we'll be able to go and look at some of these in more detail, but I can refer back to a John Hutchison sample where around one of these black hole cores there were these interfering wavelets of material, and maybe I'll revisit that for people to understand where I'm coming from. Okay, so what this means is it doesn't matter whether you're gaining energy from the vacuum gradient or you're notionally losing energy from the fractionalization of the matter that's going in. In the reforming process, if the net output is occupying less space-time than the nucleons that are born out of the system are distorting less of the physical vacuum, there will be a net energy gain. Okay, so in the overall process. And you might gain a lot of energy from the coherent process, the condensation process as it happens. Okay, so I think this is the basis behind the water car, the Stanley Meyer water car. Yes, you can use lasers as he did in his later versions and spark plugs to do the magic. This is the power behind the super flashing spark plugs, Aaron Murakami, and so forth. This is what is going on. Yes, water can be used as a fuel. It's been a deep honor to do this journey. The bonus may be that hydrocarbons are actually synthesized through this same process. And wouldn't that be ironic? Okay, so if you want to take any, give me any questions, I will answer them now. Yeah, not fossils. I mean, coal is fossils, probably. I think what happens is the basic molecules are made, probably potentially up to propane, and then those are then pressured and form longer and longer hydrocarbons under pressure and heat over time. So Boo Blazer is asking, do the isotope ratios match those found in UFO materials? Well, firstly, you have to know if they're UFO materials, so it's a bit of a question which might have a problem. Magic Sound says, during my early test with R134A gas, I only ran the MS up to mass 50. The only significant trace I saw was at mass 50, which is difluorocarbene CF2, or its anionic form CF2. Okay, so basically, as I said, Alan, I don't think there's any of that in the system, and I also don't think. In fact, did we actually show that? We did show propane. And anyway, propane doesn't really change the conclusion either. Essentially, we have one major test to do, and that is to use a CO2 scrubber on samples from the gases from the Henk urine VEGA experiment. I actually want to read through what Henk wrote here. He said, I created the specific experiment and it stopped all the time. Stopping means he created this experiment to, I think he was trying to produce gas or to do something. But anyway, he says, I created this specific experiment and it stopped all the time. Stopping means almost always too much gas in the reactor. With too much gas, the blue glowing cathode disappears and it's over. So he wants the blue glowing cathode because that's when it's in corona discharge and that's when it appears to produce a lot of excess heat. Pumping is the only way to get it started again. That is what I did. When I shut down the plasma, the pressure was relatively stable. No leaking of the tank. When I switched it on, I had to pump it again. So then I realized I had something interesting, impossible going on. The plasma did not do this before. The only difference was the big brass anode. I bought a new pump, a diaphragm pump. That is not a strong pump, but it does not contaminate the gas from the tank. There was a bonus also. Because the pump is not strong, I could leave the pump running 24 hours and more, and so also the plasma. I had a stable process going on. Then I could start collecting the gas. A thin hose on the output of the pump in a water container gave one bubble of gas every 5 minutes or so. So it took 5 minutes to create one bubble of gas. These bubbles went into the glass bottles you can see in the video. I filled the bottles with water and then the gas pushed away the water. I put a lid on the bottle in the water so no air could have come into the bottles. Now it's become interesting. The bottles have approximately the same gas mixture. I did not add any gas during this experiment. That is to say, he didn't add any hydrogen, he didn't add any propane or whatever. It was a long-running experiment that he, in his opinion, had been fully degassed. I had to pump all the time. I used this tank already for a long time, so degassing is not realistic anymore. So let's do some calculations. The pressure is about 5 millibar in the tank. So bringing it into atmospheric pressure, the gas is compressed 200 times. I have produced much more gas than in these 3 bottles before I realized this anomaly. Okay, so basically he saw that there was a lot of gas being produced before he started storing them in these 3 bottles. I have been producing at least another 3 bottles. I don't know the exact content, but let's assume it is 100 ml per bottle. Then I produced 100 times 600 milliliters of atmospheric gas. So 0.6 of a litre times 200 times expansion equals 120 litres of vacuum gas. The content of the tank is approximately 30 litres. That means the plasma has produced at least 4 times the whole content of the tank. So the production diluted the original gas mixture. It seems the tank was producing this gas in these 3 bottles. Okay, so what you could say, if we are to believe this by Matsumoto, is that something in the tank is causing electronuclear collapse. I would argue it's the fractal toroidal moment, the topological monopole, that causes the collapse of matter, and it causes it to fragment, okay? And then it goes through a wormhole and creates hydrogen, carbon, and oxygen. And these things are then compressed in other structures that then produce, or just simply burnt, to produce water and CO2, and or nuclear or coherent energy transformed inside the core to produce the observed elements that we see, and isotopes of elements, and possibly even hydrocarbons. So is the hydrogen, carbon, and oxygen produced by the electronuclear collapse, in my view, cluster decay? And does this then lead to hydrocarbon fragments like acetylene, ethane, and propane? Or is the propane coming from something else? But we have to explain these massive increases in what would appear to be heavy CO2. CO2 being incredibly stable. What do I mean by that? I mean that CO2 is more stable than H2O, which is more stable than O2. Okay? So once CO2 is formed, it's just going to stay there. It's actually more stable than the mass equivalent organic chemicals that might also account for those masses. Right. Yes, Paul, it was just air in the Vega to start. Yes. And then that was pumped down to very low pressure. Okay. So there would have been residual moisture, that is residual water, and then there would have been some nitrogen and oxygen, but very, very low concentrations. Okay. Air eating MHD, it's water eating, but it's also water producing. This is a system that produces, I've called it the flower of life for a very long time. And I believe now it 100% is the flower of life. Why? Because it produces hydrogen, oxygen, and carbon. And what do we need? We need carbohydrates or hydrocarbons, preferably carbohydrates, which have hydrogen, carbon, and oxygen. And we breathe O2. Okay? And then plants need CO2, which is what we expel, and they and also this process will likely produce CO2 as well, and they need a source of water. So life needs hydrogen, carbon, and oxygen. Okay? So this system, I believe, is taking whatever and is making hydrogen, carbon, and oxygen. It's literally the flower of life. We could Jovilicea, yes, we could make anything with it. You need to build the fractal toroidal structure, and you need to energize it and feed it. The easiest things to feed it with are oxygen and atomic hydrogen. In fact, those things will both come out of water. Have you ever taken a closer look at the Dalgnorsk crash parts on the George Knapp? They show iron crenellated microspheres plus heavy elements in interesting ratios. I'm sure they do. I think we are probably going to get to full coherent energy transformation, propulsion, teleportation, matter synthesis, matter desynthesis, radioactive waste remediation faster than we're going to settle the debate about whether some other people have done that already at another point in the universe. Okay, so I'm going to do a quick settle review of this today if there's no questions. Okay, so this was VEGA gas analysis discussion. We showed a rather lovely video sent by Henk Uren very recently here. I like it a lot.
Interesting.
I don't really want to talk over Henk, but I love the 4 quadrants here that get produced.
This is fascinating.
Thank you to my colleague and friend Alan Goldwater for hosting myself and my family and working with me on analysing these gases, doing such a diligent job, making sure everything was working before we arrived. The noise floor here is well above the noise, and that is what we based. We did the averaging of the data. This was the background air, which was basically a background air signature with slightly high CO2 because we're indoors. Then these are the elements that came out of it, and we established in, well, rather I established by working through all the possible molecular things that there's massive increase in hydrogen. You can't, this is not really a viable number because it's based off a negative number here. So this is actually an incredibly large number. It's many orders of magnitude higher than basically 0 hydrogen in the atmosphere. And the same thing is true of the carbon. These two are massively higher than the atmosphere. The 15 signal goes up. This one goes up. This could be heavy oxygen water. It would be in line with the work of Binger and Huang. The only of the oxygen isotopes that goes up is 33 here, and that would be heavy hydrogen. Sorry, this would be heavy oxygen rather. Okay, so this would be 016, 017. Okay, this goes up from its baseline, and then over here, many orders of magnitude for both potentially C160, 170, and C170, 170 heavy oxygen isotopes. This is completely in line with Binger and Huang's observations that came out of my prediction for the reaction going on in his reactor that was producing the excess heat that we published at the beginning of last year. And essentially, he observed heavy oxygen with O17. In fact, we go down to the conclusion. It's probably the best place to see it. Neon 22 and CO2 were observed to exist. He eventually did a flame test to show the spectral line of neon 22. For some reason, maybe the calcium 44 is forming less, and the structures break up, and so they release the neon 22. It might just be an aspect of working in water. And CO2 obviously is extremely stable. But we also get the carbon, oxygen 16, oxygen 17 there, and also H2O 17, heavy oxygen water, and 16O, 17O. So the one that's most easy for us to confirm is the heavy isotopes of CO2 by scrubbing the gases from more samples provided by Henk Uren. And or to do real-time testing by bringing either the mass spectrometer to the a VEGA experiment or a VEGA experiment to a mass spectrometer. Okay, so we also find the reaction blah blah blah. Gas contents in observations detected CO2 and isotopes 22 neon, H2O 17, heavy CO2 and heavy O2. So what this says is 2 systems that produce iron-rich crenellated microspheres with titanium spewing out of them and magnetohydrodynamic-based structures. They are producing heavy oxygen, heavy CO2, and heavy 17 oxygen water. I believe that we have established the real fuel source or part of the process. I still maintain there's vacuum decay going on and possibly even baryon collapse. And also the other thing that I mentioned of electron synthesis and capture from the ether. But definitely this is part of the story of what powers ball lightning, in my opinion, and leading ultimately in a normal scenario to the production of silicon, oxygen, calcium, and iron in abundance, which are almost all of the mass of the Earth, and the rest is the flower of life. Yes, Overwhelmed Games. Evo Labs call will be on Wednesday. Yeah, and Paul, this is a great support for your invention, which I guess we can talk about moving forward. And when you understand what Paul has done and what he's already observed in context, then I think it's done. I think it's done. The power source behind ball lightning and cavitation, the principal power source, because it can use any matter. The system can use any matter, but oxygen and hydrogen really get this thing going, really get it going, and that it can be initiated by cavitation. And so it explains the water car, it explains all of these systems, and there we go. It's been a really deep honor to be doing this process, and I have more absolutely stonking data from analysis done in Alan's lab, which I hope to get out in the next couple of weeks. I hope to also finish the editing of the book for Matsumoto, try and get the PDFs out next month, because I have just one more week to submit my paper for ICCF 26, and I really want to do that for the poster, because I think people, I want a lot of critical eyes on my understanding that was presented in ICCF 26. And with this kind of data, you know, I'm either wrong, and for some reason this does match the data of Binzhuan Huang. And by the way, we've recorded everything live. You can see it, so it is what it is. And I didn't start analysing it till earlier this week. And if it is true, then just like every single experiment that Binzhuan Huang produces, it produces the same kind of products. And everything that we do in the VEGA experiment, it produces the same kind of thing. If the physical manifestations are the same, I expect the gases to be the same. And so I don't expect anyone that is serious about investigating this to find different observations. I think this is what it is. So I will say thank you very much for your time. Thank you also to Black Tie for that £20 donation. It's very kind of you. And I will see you on Wednesday. Buenas noches, dobranoc, good night.